Hi, my name is Thomas Hetzinger and I'm a PhD student at the Computer Vision Lab at the Technical University of Vienna. I'm very happy to present our paper, A Fast, Unified System for 3D Object Detection and Tracking, or FUSed in short. Let's take a look at the main contributions of our paper. First, FUSed seamlessly integrates both 3D object detection and tracking into a single neural network, thus enabling end-to-end training. Second, FUSed is extremely fast. We achieve up to 10 times higher inference speed compared to other state-of-the-art object detection methods, thus making it suitable for real-time inference on the edge. And third, we propose a number of improvements to detection performance, including an auxiliary orientation estimation loss, the use of global context for tracking, and a novel dense target assignment scheme. Here is a basic overview of the FUSed network architecture. By default, FUSed takes a sequence of depth frames as input. Since we assume a static camera setting, we can compute a fast background model to separate moving objects from static ones. We pass on a stack of the most recent frame as well as exponentially averaged mean and standard deviation of previous frames onto the object detection stage. Let's take a look at the object detection stage in more detail. We use a fast 2D CNN backbone for feature extraction. However, since we want to do detection in a 3D space, the features must be lifted from 2D to 3D space, which is done in a separate 2D to 3D module. The result is a 4D feature tensor, which can be imagined as a subdivision of the sensor's field of view in a three-dimensional grid of cells, as shown in the bottom right, where for each cell we have extracted a one-dimensional feature vector. Based on this 4D tensor, we can compute three things. First, a global context vector, which is passed on to the tracking stage. Second, we train the network to estimate the camera pose. While for inference we assume that the camera intrinsics are known, we find that training the network to predict the camera pose leads to more accurate results. Third, we predict preliminary bounding box proposals. If the application does not require tracking over time, then these proposals can already be used as outputs. The computed global context vector, camera pose estimation, and preliminary proposals are passed on to the tracking stage, which we can also look at in more detail. The cell features extracted in the object detection stage now take on the roles of tokens. As an initial pre-processing step, tokens representing empty space are filtered out to reduce processing load. Afterwards, the remaining tokens are augmented with positional encodings. This is possible since we can associate a location in 3D space with each token. Tracked entities are represented by both object and track queries. Object queries are designed to capture entities that have newly appeared in the current time step. Object queries are computed dynamically using an MLP that takes an object query index and the previously computed global scene context as input. Track queries, on the other hand, represent entities that have already existed in the previous time step and have been passed on. Both object and track queries are then updated in a perceiver model with the tokens extracted in the object detection stage. Afterwards, the tokens are projected down to bounding boxes, and those above a certain confidence threshold represent the outputs of our FUSed model. The corresponding track queries are passed on to the next time step. As shown on the right-hand side, the FUSed model produces trajectories of oriented bounding boxes as outputs. Let's now move on to the experimental section of our paper. First, we compare the object detection performance of our model against the state-of-the-art. We compare the FUSed model without the tracking stage against VoltNet, Point Pillars, H3DNet, Group 3 and the baseline model of the MIPD dataset paper. Here the first 4 rows in the table represent models that are not optimized for runtime, as can be seen on the right-hand side. Their runtime is more than 10 times slower than our model. The last 2 rows are optimized for runtime, and we can see that the FUSed model outperforms the reference model in all metrics. Mean average position, mean average heading similarity, and frames per second numbers both on an NVIDIA Titan X and the Jetson Nano edge device. Moving on to our object detection ablation study, we can see that all of our design choices are justified. The modifications made have minimal impact on FPS numbers, with the notable exception of the 2D to 3D conversion block, where the FPS number drops by 1.3, however object detection metrics increase between 4 and 6%. When comparing the FUSed model without a tracker to FUSed with a tracker, the FPS drops to 6.4, however object detection metrics significantly improve. Here we take a look at the tracking ablation study and the tracking comparison against the state-of-the-art. The state-of-the-art is represented by the deep sort tracker, which has been combined with the FUSed detection stage. As we can see in the table, FUSed outperforms the others in most metrics. Thank you for your attention.